What if everything we think we know about the universe is built on a fundamental misunderstanding? Picture this: a single number etched into the fabric of reality itself, the speed of light, the cosmic speed limit that shapes everything from the way stars shine to the way time flows. For centuries, scientists have treated it as an unchanging truth, a constant so reliable that it defines the very equations that explain our existence. But what if that constant isn't so constant after all? What if, across the vast stretches of deep time, light itself has been playing tricks on us, slowing down or speeding up in ways that rewrite the rules of physics? This isn't just a thought experiment, it's a possibility that could shatter our understanding of the cosmos. Think about the last time you looked up at the night sky. Those pinpricks of light, some of them traveling for billions of years to reach your eyes, carry secrets older than Earth itself. But what if those beams of light weren't always moving at the same speed? What if the universe, in its infancy, allowed light to race faster, or in its twilight years, forces it to crawl? The implications are staggering. The age of the universe, the distance to far-off galaxies, even the nature of time and space, all of it could be different than we've ever imagined. This isn't just about tweaking a few equations, it's about peeling back the curtain on reality and asking whether we've been reading the cosmic script all wrong. So let's take a journey not just through space but through time itself. We'll start at the dawn of the universe, when the first flashes of light burst into existence, and follow their path across eons, watching as the very laws of physics might have shifted beneath our feet. We'll explore the wild theories that suggest light's speed could change, the daring scientists who have challenged the status quo, and the mind-bending consequences if they're right. By the end, you'll see the cosmos in a whole new light, literally. This is more than a story about physics. It's a story about how we uncover the truth, and how sometimes the universe's greatest mysteries are hiding in plain sight. Ready to question everything? Let's begin. To understand why the speed of light holds such sacred status in physics, we have to rewind to the late 19th century. Picture Albert Michelson and Edward Morley, two scientists meticulously measuring light's speed, expecting to find variations as Earth moved through the hypothetical luminiferous ether. Instead, their experiments revealed something startling. No matter how they measured it, light's speed remained stubbornly unchanged. This discovery became the bedrock of Einstein's theory of relativity, cementing light speed as nature's ultimate constant. But here's the twist: what if their experiments only captured a snapshot of a much larger, evolving story? The idea that light speed could vary over cosmic time isn't as far-fetched as it sounds. Some theories, like those proposed by physicist Joe Megiddo, suggest that in the searing heat of the early universe, light might have traveled faster, breaking its own speed limit to solve cosmic puzzles like the Horizon problem. Why does the universe look so uniform in every direction if light hadn't had enough time to smooth things out? A variable speed of light could be the missing piece. Then there's the tantalizing evidence from distant quasars, ancient beacons of light, whose spectral lines seem to hint at subtle shifts in physics' fundamental constants over billions of years. Could those shifts include light speed? Yet skeptics argue these anomalies might just be measurement errors or gaps in our understanding of astrophysics. After all, tampering with light's constancy sends tremors through everything. The age of the universe, calculated using today's speed of light, would suddenly be up for debate. Distances to far-off galaxies, the behavior of black holes, even the very structure of space-time, all of it would need re-examination. It's like discovering the ruler you've used to measure the cosmos has been stretching and shrinking all along. So where does that leave us? In a thrilling gray zone where the universe's deepest truths might still be hiding in plain sight. Whether light speed is an unwavering constant or a cosmic chameleon, the debate itself reminds us that science is never truly settled. It's a living, breathing journey into the unknown. And that's what makes this question so electrifying. The answers, if they come, won't just rewrite textbooks, they'll redefine reality. Before Einstein rewrote the cosmic rulebook, our understanding of light was a patchwork of brilliant but incomplete ideas. Isaac Newton imagined light as a stream of particles, while James Clerk Maxwell's equations revealed its wave-like nature, linking electricity and magnetism in a dance that predicted light's speed with stunning precision. Yet even Maxwell couldn't have guessed how his work would collide with a deeper truth. Then came Einstein in 1905, turning physics upside down by declaring light's speed the universe's one true constant, a fixed point in a sea of relativity. His theory didn't just solve puzzles, it became the foundation for everything from GPS satellites to black hole physics. But buried in this triumph is a tantalizing question. Did Einstein's breakthrough blind us to other possibilities? History whispers hints that light's behavior might not always align with our textbooks. Ancient astronomers like Ptolemy recorded celestial events that, when recalculated with modern tools, sometimes show puzzling discrepancies. Could these be cosmic breadcrumbs, suggesting light speed wasn't always 299,792 kilometers per second? Even Einstein himself, in private correspondence, pondered whether constants might evolve over time. The irony is thick. The man who cemented light's constancy also left cracks in the foundation for future explorers. Fast forward to today, and those cracks are widening. Researchers combing through centuries of eclipse records and supernova observations have spotted anomalies that defy easy explanation. One team studying light from distant quasars found subtle shifts in atomic spectra, as if the rules of physics themselves were slightly different billions of years ago. Another group analyzing the cosmic microwave background, the afterglow of the Big Bang, found patterns that a variable speed of light could neatly explain. These aren't just statistical glitches, they're potential windows into a universe far stranger than Einstein imagined. Yet the scientific establishment pushes back, and for good reason. If light speed changes, the ripple effects would be catastrophic for our models. The age of stars, the expansion rate of the universe, even the way atoms bond, all would need recalibrating. It's like discovering your watch runs differently depending on the weather, throwing every appointment into chaos. But here's the beauty of science, it thrives on chaos. Every revolutionary idea, from plate tectonics to quantum mechanics, began as heresy. The real question isn't whether Einstein was wrong, it's whether we're brave enough to keep questioning the answers we hold sacred. What makes this debate so electrifying isn't just the science, it's the human drama behind it. Picture the young postdoc sweating over telescope data that contradicts a century of dogma, or the veteran theorist risking reputation to explore an idea others dismiss as fringe. This is how science moves forward, not in tidy leaps, but in messy, thrilling stumbles toward the truth. Whether light speed is eternal or evolving, the search itself reminds us that the universe always has another secret to share. And that's why this story isn't just about physics, it's about our endless hunger to peel back the next layer of reality. Here's a cosmic puzzle that stumped scientists for decades, the faint young sun paradox. Rewind 4 billion years and our sun would have been 30% dimmer than it is today. By all accounts, Earth should have been a frozen wasteland, a snowball hurtling through space. Yet the geological record tells a different story. Ancient rocks show evidence of liquid water, even thriving microbial life. How could a planet so warm exist under such a feeble star? It's a contradiction that's lingered like a thorn in the side of astrophysics. But what if the answer lies not in the sun's behavior, but in light itself? Imagine light in the early universe sprinting faster than it does today. If photons traveled at greater speeds, they'd pack more energy like a cosmic delivery truck hitting the gas pedal. That extra kick could have heated Earth's surface just enough to offset the sun's weakness, creating the Goldilocks conditions life needed to emerge. It's a radical idea, but not without precedent. Some models of quantum gravity suggest that in the extreme density of the early cosmos, the fabric of spacetime might have been more malleable, allowing light to break its own speed limit. Think of it like running through water versus running through air. The thickness of space itself could have changed over time. The evidence isn't just theoretical. Take the light from quasars, the brilliant cores of ancient galaxies. When scientists analyze their spectra, they sometimes detect subtle shifts in the fine structure constant, a number that hinges on the speed of light. If that constant was different billions of years ago, it would imply light's speed was too. Even Earth's own climate history fits the puzzle. Periods of unexpected warmth align eerily with epochs where light's behavior might have deviated. It's as if the universe left us breadcrumbs in the form of contradictions, waiting for us to connect the dots. Of course, not everyone's convinced. Critics argue that alternative solutions, like a thicker greenhouse atmosphere or changes in Earth's orbit, could explain the paradox without upending physics. And they're right to be cautious. Tweaking the speed of light isn't just adjusting a dial, it's rewiring the cosmic circuit board. Yet that's what makes science so thrilling. The faint young sun paradox isn't just a gap in our knowledge, it's an invitation to question the very constants we take for granted. Whether light speed is the key or just another red herring, one thing's certain: the universe loves keeping us on our toes. And that's why this mystery isn't just about solving a puzzle, it's about learning how to ask better questions. At the tiniest scales imaginable, the universe is anything but empty. What looks like void to our eyes is actually a bubbling cauldron of quantum activity, where particles flicker in and out of existence so fast they defy measurement. This isn't just theoretical speculation, it's a phenomenon we've observed in labs, where the so-called empty space between atoms crackles with unpredictable energy. Scientists call it quantum foam, and it's here that our story takes a strange turn. Because if even the vacuum of space isn't truly empty, could this seething quantum sea be subtly tugging at light itself, altering its speed over cosmic time? Think of space like an invisible ocean, with light as a swimmer cutting through the waves. Today, that swimmer moves at a steady pace, 299,792 kilometers per second. But what if the ocean itself has been changing? Quantum field theory suggests the vacuum of space holds energy, a kind of background hum that permeates everything. Some models propose this vacuum energy was stronger in the early universe, like thicker water slowing down our swimmer. Over billions of years, as the universe expanded and cooled, that energy might have diluted, subtly changing how light propagates. It's as if the rules of the race weren't fixed, the track itself was evolving. The evidence for this wild idea comes from some of the most precise measurements in physics. When scientists examine the cosmic microwave background, the faint glow left over from the Big Bang, they've spotted tiny irregularities that standard models struggle to explain. One possibility: quantum fluctuations in the early universe's vacuum energy left fingerprints on that ancient light, hints that space itself behaved differently back then. Even more intriguing are lab experiments with Casimir plates, two metal surfaces placed incredibly close together in a vacuum. At these microscopic distances, the plates are slightly pushed together by quantum forces, proving that empty space exerts real, measurable pressure. If that pressure isn't constant across time, why should light speed be? Yet the implications are dizzying. If vacuum energy affects light speed, then every calculation we've made about the universe's age, size, and expansion could need recalibration. Distant supernova might not be where we think they are. Black holes could behave in unexpected ways. It's like discovering the air has been thicker at high altitudes all along, throwing off every altimeter reading in history. The beauty of this idea isn't just in its audacity, it's in how it ties together two of physics' greatest mysteries, quantum mechanics and the nature of light. Skeptics, of course, have good reasons to pause. Quantum fluctuations are notoriously slippery to measure, and attributing changes in light speed to them risks opening Pandora's box. Without airtight evidence, it's easy to drift into speculation. But that's where the next generation of experiments comes in. Projects like the James Webb Space Telescope are peering deeper into the early universe than ever before, hunting for subtle shifts in ancient starlight that might reveal quantum vacuum's fingerprints. Others are refining lab techniques to measure vacuum energy with unprecedented precision, searching for hints that it's not as constant as we assumed. What makes this quest so compelling isn't just the science, it's the philosophical shift it demands. For centuries, we've treated space as a static stage where the drama of physics unfolds. But if quantum foam can influence light speed, then space itself becomes an active player, shaping the laws we once thought immutable. Whether this idea holds up or not, it reminds us that the universe is far stranger and far more dynamic than our textbooks suggest. And that's the real thrill of science, not just answering questions, but discovering how much more there is to ask. Paul Dirac was no stranger to shaking up the scientific world. The man who predicted antimatter and reshaped quantum mechanics with his groundbreaking equations also harbored a quiet fascination with the idea that nature's constants might not be so constant after all. In the 1930s, while most physicists were content to treat numbers like the speed of light as fixed pillars of reality, Dirac dared to ask a dangerous question. What if these so-called constants were slowly drifting over cosmic time? His reasoning was deceptively simple. When he compared the ratio of the electromagnetic force to gravity, he noticed something peculiar. The numbers seemed to line up in a way that suggested a deeper, hidden relationship. To Dirac, it was as if the universe was whispering a secret. The fundamental forces might be evolving together, and light speed could be part of that dance. At the time, the idea was met with skepticism, even ridicule. After all, Einstein's relativity had enshrined light speed as the ultimate constant, the one unshakable rule in a universe of variables. But Dirac wasn't one to back down from a paradox. He proposed what's now called the large numbers hypothesis, suggesting that the apparent coincidence between cosmic ratios wasn't accidental. It was evidence of a deeper, time-dependent connection between constants. Imagine a universe where the strength of gravity, the charge of an electron, and even the speed of light were subtly shifting in lockstep, like gears in a cosmic clockwork. It was a vision of physics far more dynamic than anyone had imagined. Fast forward to today, and Dirac's once heretical ideas are experiencing a quiet revival. Modern astronomers studying distant quasars have detected faint anomalies in the light from these ancient objects, shifts in spectral lines that hint at possible variations in the fine structure constant, a number intimately tied to light speed. Meanwhile, theories like Joe Megiddo's variable speed of light cosmology explicitly build on Dirac's intuition. suggesting that light might have raced faster in the early universe to solve lingering puzzles like the horizon problem. Even string theory, with its extra dimensions and vibrating brains, allows for scenarios where constants could vary across different epochs or regions of space. Yet the debate is far from settled. Critics argue that the evidence for varying constants remains ambiguous, buried in the noise of measurement uncertainties and astrophysical complexities. They point out that tweaking light speed doesn't just tweak physics, it upends it. The cosmic distance ladder, the age of stars, even the behavior of black holes would all need re-examination. It's like realizing the ruler you've used to map the universe was made of rubber all along. But that's precisely why Dirac's ideas endure not as settled truth, but as a provocation. They remind us that science advances not by guarding old certainties, but by daring to question them. What makes Dirac's legacy so compelling isn't just the science, it's the mindset. Here was a man who could stare at a set of numbers and see not just equations, but a story waiting to be told. Whether his hunch about varying constants proves right or wrong, it's a testament to the power of curiosity. Because sometimes the most revolutionary ideas aren't the ones that give us answers, they're the ones that keep us asking better questions. And in a universe as mysterious as ours, that might be the most valuable constant of all. Einstein's theory of relativity is like a cosmic symphony with the speed of light as its unwavering conductor. Every note time dilation, length contraction, the bending of spacetime depends on that one constant beat. But what happens if the conductor's tempo changes? If light speed wasn't always the same, would the symphony fall into chaos, or would the universe simply compose a new harmony? Take time dilation, the mind-bending effect where clocks tick slower near massive objects or at high speeds. This isn't just theory. GPS satellites correct for it daily, adjusting their clocks because gravity and motion literally warp time. But if light speed were different in the past, those distortions might have played out in ways we've never imagined. Picture a young universe where light raced faster. Time itself could have flowed differently, stretching or compressing in ways that leave fingerprints on ancient starlight. Some cosmologists even speculate that variable light speed might explain why the universe's expansion is accelerating, the very mystery we call dark energy. It's as if we've been listening to the cosmos with earplugs, and now we're finally starting to hear the full, strange melody. Then there's length contraction, relativity's other head spinner, where objects shrink in the direction of motion at near light speeds. If light speed wasn't fixed, those rules might have flexed over cosmic history. Imagine a galaxy hurtling through space billions of years ago, its shape distorted not just by its velocity, but by a universe where the speed limit itself was shifting. Even black holes, those gravitational monsters born from Einstein's equations, might have behaved differently, their event horizons swelling or shrinking as light speed changed. The math gets dizzying fast, but the tantalizing possibility remains. Our universe's deepest quirks could be clues to a physics far more fluid than we thought. Yet the real shock isn't that relativity might break. It's that it might bend instead. Some theories, like scalar tensor cosmology, suggest that a varying speed of light could integrate seamlessly into Einstein's framework, tweaking the equations without tearing them apart. Think of it like updating an old map. The landmarks stay the same, but the distances between them shift. This isn't about discarding relativity. It's about revealing hidden layers, like finding out your favorite song has a remix you never knew existed. That's the thrilling tension at the heart of this idea. Physics isn't a static rulebook, it's a living dialogue between observation and imagination. Whether light's constancy holds or falters, the real lesson is how much we still have to learn. Because the universe doesn't care about our textbooks, It's too busy writing its own story, one mysterious chapter at a time. Imagine a photograph taken just moments after the birth of the universe, a blurry, glowing imprint of that first cosmic dawn. That's the cosmic microwave background, or CMB, a faint whisper of radiation lingering from the Big Bang itself, stretching across the entire sky. This ancient light has traveled nearly 14 billion years to reach us, carrying secrets about the universe's infancy. But here's the twist. If the speed of light wasn't constant when this light first burst forth, the CMB might not just be a snapshot. It could be a hall of mirrors, distorting the past in ways we're only beginning to suspect. The patterns etched into the CMB are like cosmic hieroglyphics, tiny fluctuations in temperature that tell the story of the universe's earliest structures. Scientists have pored over these patterns for decades, mapping them with exquisite precision using satellites like Planck and WMAP. But buried in that data might be anomalies, subtle asymmetries, or unexpected clumps that don't fit the standard model. Some researchers argue these irregularities could be hints that light speed was different when the CMB formed. Picture a frozen pond where the ice isn't uniformly thick. The cracks and bubbles might reveal how fast the water was flowing when it froze. Similarly, the CMB's imperfections could betray a universe where light once traveled faster or slower, warping the very fabric of space-time before settling into today's rhythm. One tantalizing clue comes from the so-called axis of evil, a mysterious alignment of temperature fluctuations in the CMB that seems to defy randomness. Could this be a relic of a time when light's behavior was fundamentally different? Or take the lingering discrepancies in measurements of the Hubble constant, the rate at which the universe is expanding? Depending on whether we calculate it using the CMB or nearby supernova, we get slightly different answers. A variable speed of light could help bridge that gap, like adjusting the tempo of a song to match two out-of-sync instruments. Yet proving this idea is a monumental challenge. The CMB is incredibly faint, its signals buried under layers of cosmic noise and foreground interference. Distinguishing a true anomaly from a measurement artifact is like trying to hear a single violin in a thunderstorm. Even if the data shows oddities, they could have mundane explanations: dust clouds, galactic emissions, or quirks in our instruments. That's why some physicists are turning to next-generation telescopes, like the Simons Observatory or CMB-S4, which promise unprecedented sensitivity. These tools might finally spot the telltale distortions that earlier missions could only guess at. What makes this search so electrifying isn't just the science, it's the philosophical stakes. If the CMB holds evidence of a shifting speed of light, it wouldn't just tweak our models, it would force us to rethink how we measure time and distance across the cosmos. The age of stars, the size of galaxy clusters, even the nature of dark energy, all could be up for reinterpretation. It's like discovering that the ruler you've used to map the universe has been subtly expanding or contracting all along. Skeptics, of course, caution against jumping to conclusions. The standard model of cosmology, built on Einstein's relativity, has survived every test thrown at it for over a century. Dismantling it would require extraordinary evidence, not just intriguing anomalies. But that's the beauty of science at the frontier. It thrives on tension between the known and the unknown. Whether the CMB's secrets confirm light's constancy or reveal its hidden flexibility, one thing's certain: the universe is still writing its rules, and we're just beginning to decipher them. Some of the most daring ideas in physics start with a simple question: what if we've been looking at the problem backward? That's exactly what physicist Joe Megiddo and his colleagues asked when they proposed variable speed of light cosmology, a theory that flips conventional wisdom on its head. Instead of assuming light speed has always been locked at 299,792 kilometers per second, they imagined a younger, wilder universe where photons raced across space at breakneck speeds, far faster than they do today. It's a radical notion, but one that could solve some of cosmology's stickiest puzzles without relying on the usual fixes. Take the horizon problem, a head-scratcher that's puzzled scientists for decades. When we look at the cosmic microwave background, the afterglow of the Big Bang, we see a sky that's almost perfectly uniform in temperature, no matter which direction we point our telescopes. But here's the catch. According to standard physics, there hasn't been enough time since the universe began for heat to travel between these distant regions and even things out. It's like walking into a room where two cups of coffee placed at opposite ends have somehow cooled to the exact same temperature without anyone stirring them. The usual solution is cosmic inflation, a theory proposing the universe expanded exponentially faster than light for a split second after the Big Bang. But what if inflation isn't the only answer? VSL cosmology offers a different path. If light traveled much faster in the early universe, it could have zipped between distant regions before they drifted apart, smoothing out temperatures like a cosmic blender. No need for inflation's abrupt growth spurt, just a temporary tweak to light's speed limit. The math even checks out. Megiddo's models show that a faster speed of light in the first fractions of a second after the Big Bang could produce the same uniformity we observe without invoking exotic physics. It's an elegant idea, but not without its critics. Skeptics argue that tampering with light's constancy opens a Pandora's box of complications. Einstein's relativity is built on the premise that light's speed is the one fixed point in a universe of variables. Mess with that, and everything from the age of stars to the behavior of black holes gets thrown into question. Even more troubling, VSL theories struggle to explain why light speed would have slowed down over time. Some suggest it's tied to the cooling of the universe, like molasses thickening as temperatures drop. Others propose hidden dimensions or quantum gravity effects that subtly altered light's behavior. But without direct evidence, these remain tantalizing speculations. Yet the allure of VSL cosmology isn't just in its answers, it's in the questions it forces us to ask. Science thrives on competing ideas, and sometimes the most heretical theories push us toward deeper truths. After all, Einstein himself appended Newton's centuries-old laws by reimagining time and space. Who's to say the next revolution won't come from rewriting light's role in the cosmic story? Whether VSL cosmology ultimately holds up or fades into obscurity, it reminds us that the universe is stranger than we can imagine, and that's what makes the search so thrilling. Black holes are the universe's ultimate rule breakers, places where gravity twists the laws of physics into knots. Near their event horizons, light itself bends and warps, struggling to escape the gravitational maw. But what if these cosmic monsters aren't just distorting light's path? What if they're altering its very speed? It's a possibility that sounds like science fiction, yet some theories suggest that in the extreme curvature of space-time around a black hole, the speed of light might not be the constant we've come to rely on. And if that's true, it raises an even wilder question. Could the unimaginable gravity of the early universe have permanently changed light's behavior, leaving echoes in the cosmos we see today? Picture the universe in its first moments, a seething, dense soup of matter and energy where black holes may have formed and evaporated in an instant. In conditions like these, gravity wouldn't just bend space-time, it might rewrite the rules altogether. Some models of quantum gravity propose that in such extreme environments, the speed of light could vary, like a car navigating a warped highway where the speed limit changes at every turn. This isn't just theoretical musing. Observations of light skirting the edges of supermassive black holes, like the one at the center of our galaxy, show subtle delays and distortions that don't always match predictions. Could these be hints that gravity's grip on light is stronger or stranger than we've assumed? The implications ripple outward. If light speed was different near black holes in the early universe, our measurements today might be capturing only a sliver of its true history. It's like trying to reconstruct a symphony by listening to a single note. The full composition remains hidden. This idea challenges one of relativity's core tenets, that light speed is the same for all observers, no matter their motion or the gravity they're under. Yet black holes have always been laboratories for the impossible, places where relativity and quantum mechanics collide in ways we don't yet understand. Maybe light's constancy is another casualty of that cosmic clash. Skeptics, of course, point to the mountain of evidence supporting Einstein's vision. After all, if light speed varied near black holes, wouldn't we see more dramatic anomalies in the light from quasars or pulsars orbiting them? But others counter that these effects could be subtle, buried in the noise of astrophysical chaos. The debate hinges on a deeper mystery, how gravity behaves at its most extreme. Until we can probe closer to a black hole's edge, perhaps with future telescopes or gravitational wave detectors, the question remains tantalizingly open. What makes this idea so compelling isn't just the science, it's the sheer audacity of the question. Black holes already defy intuition, warping time and space beyond recognition. If they can also bend the rules of light itself, it means the universe is even more fluid, more dynamic than we've dared to imagine. And that's the real thrill of physics. Not just solving puzzles, but discovering that the pieces might fit in ways we never expected. Whether black holes hold the key to light's secrets or not, they remind us that the cosmos still has surprises up its sleeve, and that's what keeps us looking up. Dark energy is the universe's greatest unsolved mystery, an invisible force pushing galaxies apart at an ever-increasing rate. We know it makes up about 68% of the cosmos, yet we have no idea what it actually is. But here's an even wilder thought. What if this mysterious force isn't just stretching space, but also tweaking the very rules of light itself? Imagine the universe as a rubber sheet, expanding faster and faster, and light as a ripple racing across its surface. If the sheet stretches unevenly, could that ripple slow down or speed up without us even realizing it? This isn't just poetic speculation. Some cutting-edge theories suggest dark energy might be entangled with the fundamental constants of nature, including the speed of light. In these models, dark energy isn't just a passive backdrop. It's an active player, subtly reshaping the fabric of physics as the cosmos grows. The math gets dizzying, but the core idea is startling. As space-time stretches, the rules embedded within it might stretch too. Think of it like a marathon runner whose stride lengthens as the racecourse itself expands beneath their feet. If light speed is tied to the universe's expansion, then every time we measure a distant supernova or a quasar's glow, we might be glimpsing not just the past, but a past where physics worked differently. The clues hiding in the data are faint but fascinating. Take the Hubble tension, the nagging discrepancy between how fast we think the universe is expanding based on nearby measurements versus the ancient light of the cosmic microwave background. Could this mismatch be a hint that light speed, and thus our cosmic yardstick, has drifted over time? Or consider dark energy's own eerie uniformity. It appears identical everywhere, as if it's not just filling space but redefining it. Some theorists, like those working on quintessence models, propose that dark energy could be a dynamic field, one that interacts with light in ways we haven't yet detected. It's like realizing the wind doesn't just move the trees, it might also be changing the gravity that holds them down. Of course, skeptics raise valid concerns. If dark energy were altering light speed, wouldn't we see more dramatic anomalies in the light from distant galaxies? And how could such a change square with Einstein's relativity, which treats light speed as the unshakable foundation of spacetime? These questions don't have easy answers, but that's what makes the hunt so thrilling. Science doesn't shy away from contradictions, it leans into them because that's where breakthroughs hide. What's truly mind-bending is the possibility that dark energy and light speed could be two sides of the same cosmic coin. If true, it would mean the universe's greatest mystery, the force driving its expansion, is also quietly rewriting the laws we use to understand it. That's the humbling beauty of cosmology. Just when we think we've got the universe figured out, it whispers a secret that changes everything. And whether this idea holds up or not, it reminds us that the cosmos is far stranger, far more dynamic than we've ever dared to dream. The quest to prove whether light speed has changed over cosmic time isn't just theoretical, it's a detective story written in starlight. Astronomers don't have a time machine to measure ancient photons directly, but they do have the next best thing, quasars. These brilliant beacons, powered by supermassive black holes billions of light years away, act as cosmic time capsules. Their light, traveling for eons before reaching us, carries imprints of the universe's younger days. By analyzing the spectral lines of this ancient light, the unique fingerprints of atoms like hydrogen or oxygen, scientists can hunt for subtle shifts that might betray a different speed of light in the past. It's like finding an old photograph where the colors have faded unevenly, hinting that the camera's shutter speed wasn't what we thought. But the challenge is staggering. Imagine trying to detect a change of just a few kilometers per second in light's speed across billions of years. It's like measuring whether a marathon runner's pace shifted by a single footstep over their entire race. To tackle this, researchers use the fine structure constant, a number that ties together light speed, the charge of an electron, and other fundamental forces. If this constant drifts over time, it could signal that light speed has too. Some teams, like those studying the Keck and Relativity telescopes' quasar data, claim to have spotted such shifts, tiny but tantalizing. Others argue these anomalies could stem from interstellar gas clouds or instrument quirks, not physics itself. The debate hinges on a razor's edge of uncertainty, where every new observation could tip the scales. Supernovae offer another clue. These exploding stars serve as standard candles, their brightness predictable enough to gauge cosmic distances. But if light speed varied in the past, those distances and the expansion rate of the universe derived from them might need recalculating. Discrepancies in measurements of the Hubble constant, the universe's expansion rate, could be a breadcrumb trail leading back to inconstant light. Even the cosmic microwave background, the afterglow of the Big Bang, might hide echoes of an era when photons raced faster through a hotter, denser cosmos. The real breakthrough, though, could come from labs on Earth. Quantum experiments with ultra-precise atomic clocks are testing whether fundamental constants waver over time. By comparing clocks based on different elements, scientists can detect shifts so minute they'd make a stopwatch seem crude. Meanwhile, next-gen telescopes like the Extremely Large Telescope will peer deeper into space and further back in time than ever before. They might catch light in the act of breaking its own rules, revealing a universe where the laws of physics aren't just written in stone, but in something far more fluid. What makes this search so electrifying isn't just the potential discovery, it's the sheer audacity of the question. We're asking whether the universe's most trusted constant might have been a variable all along. And whether the answer is yes or no, The hunt itself reminds us that science's greatest triumphs begin with the courage to doubt what everyone else takes for granted. The stars may yet confess their secrets, but only if we keep listening and questioning with open minds. Quantum entanglement is one of the strangest phenomena in physics, a ghostly connection that links particles across unimaginable distances, allowing them to influence each other instantly, as if space and time didn't exist. Einstein famously called it spooky action at a distance, a phrase that captures just how unsettling this idea was even for the greatest scientific minds. But here's where it gets even weirder. If the speed of light isn't the fixed constant we've always believed, could entanglement's eerie behavior have changed over cosmic history too? The answer might rewrite not just quantum mechanics, but our entire understanding of reality. Think of entanglement like a pair of cosmic dice, forever linked no matter how far apart they're separated. Roll one here on Earth, and its twin in a distant galaxy will instantly show the same result. No signal, no delay, just instantaneous correlation. This defies relativity's rule that nothing can outpace light, yet countless experiments confirm it's real. But what if light speed wasn't always the universal speed limit? Some theorists propose that in the early universe's extreme conditions, entanglement might have operated differently, its spookiness tuned to a different rhythm. Imagine a universe where entangled particles didn't just communicate instantly, but did so even faster or slower depending on how light itself behaved. It's as if the rules of quantum weirdness were written in erasable ink, subtly changing as the cosmos evolved. The clues might lie in the fine print of quantum theory. Entanglement relies on properties like spin or polarization, which are deeply tied to electromagnetism, the same force governed by light speed. If that speed shifted over time, it could have altered how entangled particles interact, leaving faint imprints in the quantum fabric. One provocative idea suggests that variations in light speed might explain why entanglement seems to ignore spacetime's usual limits. In certain quantum gravity models, spacetime itself emerges from a deeper, more chaotic quantum layer. If light's behavior was different in that primordial soup, entanglement might have been the original cosmic internet, stitching the universe together before relativity's rules even took hold. Of course, testing this idea is a monumental challenge. Unlike quasars or supernova, we can't observe quantum states from billions of years ago directly. But cutting-edge lab experiments might offer a workaround. By recreating high-energy conditions similar to the early universe, physicists could simulate how entanglement behaves when fundamental constants are tweaked. Other teams are probing the cosmic microwave background for statistical anomalies that might hint at ancient quantum correlations, echoes of a time when entanglement's spookiness operated by different rules. Skeptics argue that entanglement's non-locality is a fundamental feature of quantum mechanics, untouched by the speed of light or any other variable. To them, spooky action is just that, spooky but immutable. Yet history shows that even the most bedrock principles can bend under scrutiny. Whether entanglement's mysteries are tied to light's inconstancy or not, the mere possibility forces us to confront a deeper truth. The universe's rulebook might be far more flexible than we've ever dared to imagine. And that's where the real magic happens, not in the answers we find, but in the questions we're finally brave enough to ask. What if our universe's speed of light isn't just a quirk of physics, but a cosmic accident? The multiverse theory throws open the door to a staggering possibility. Countless other universes, each with its own unique laws, where light might zip faster, crawl slower, or even behave in ways we can't fathom. Imagine a cosmos where photons move like molasses, stretching seconds into eternities, or another where they flash past in an instant, rendering time itself meaningless. In this sea of alternate realities, our universe's steadfast 299,792 kilometers per second could be nothing more than a lucky roll of the dice. The idea isn't pure fantasy. Certain branches of string theory suggest that the fundamental constants we take for granted, like the speed of light, could be frozen into place during a universe's birth, the result of quantum fluctuations or higher dimensional geometry. Picture a vast cosmic landscape where each universe is a bubble with its own unique physics, shaped by the random tug of invisible forces. In some, light speed might be slower, turning stars dim and lifeless. In others, it could be faster, sparking frenzied particles and temperatures too extreme for matter to coalesce. Ours, then, would be the Goldilocks zone, not just for life, but for the very stability of physics itself. Yet the real mind-bender isn't just that other universes could exist with different light speeds, it's that we might never know. The multiverse, by definition, lies beyond our observational reach, sealed off by horizons even light can't cross. But here's the twist. If these alternate realities left faint imprints on our own cosmos, like echoes in a hall of mirrors, we might find clues. Some theorists hunt for anomalies in the cosmic microwave background, strange patterns or asymmetries that could hint at collisions with other universes in the distant past. Others probe quantum mechanics for signs of leakage between realities, subtle nudges that might betray a deeper interconnectedness. Of course, skeptics dismiss this as untestable speculation, and they're not wrong. Without direct evidence, the multiverse remains a dazzling hypothesis, not a proven fact, but that's precisely why it's so compelling. It forces us to confront the arrogance of assuming our universe's rules are the only ones that matter. After all, every time humanity has declared something a universal constant, the Earth, as the center of the cosmos, Newton's absolute time, we've been humbled by discoveries that shattered those assumptions. Whether the multiverse is real or not, the thought experiment alone reshapes how we see our place in existence. If light speed isn't a sacred law but a local byproduct, it means the universe isn't just stranger than we imagine, it's stranger than we can imagine. And that's the true power of this idea, not to give answers, but to remind us how much wonder lies in the questions we've yet to ask. If the speed of light isn't the unwavering constant we've built our understanding of reality upon, then what does that say about reality itself? For centuries, science has operated under the assumption that certain laws, like light's unbreakable speed limit, are fixed pillars, giving us a stable foundation to measure everything from the age of stars to the fabric of spacetime. But if that pillar turns out to be more like a pendulum, swinging subtly over cosmic time, then the very notion of objective truth starts to wobble. It's not just physics at stake, it's philosophy. If the universe's rules can change, then what, if anything, is truly eternal? Consider time, that relentless river we all float on. In Einstein's relativity, time isn't absolute. It bends near massive objects or at high speeds. But if light speed shifts, so does the relationship between time and space. A faster speed of light in the early universe could mean time itself flowed differently, stretching or compressing in ways that rewrite the cosmic calendar. Suddenly, the age of the universe isn't a fixed number, it's a moving target dependent on an ever-shifting constant. Even causality, the idea that cause must precede effect, could blur. If light speed isn't constant, does the past still reliably lead to the present? Or could the rules of sequence themselves be up for grabs? Then there's the unsettling question of whether physical laws are discovered or invented. Science has always treated its constants as universal truths waiting to be uncovered, like buried treasure. But if those truths evolve, then the laws we've etched into textbooks might be more like snapshots, freeze frames of a deeper, dynamic process. Imagine a universe where the rules of chemistry or gravity weren't just written once, but are constantly being revised by some unseen hand. It's as if we've been studying a painting, convinced it's finished, only to realize the artist is still adding brushstrokes. This isn't just abstract musing, it reshapes how we see our place in existence. Human civilization has built its myths, its sciences, even its technologies on the idea of a predictable cosmos. The sun will rise, atoms will bond, light will always travel the same speed. But if the universe is more improvisation than script, then our quest for understanding becomes a dance with a partner who keeps changing the steps. Maybe that's the real lesson, not that reality is slipping through our fingers, but that it was always more fluid than we dared to believe. And in that uncertainty lies not chaos, but possibility, a universe still surprising itself and us with every passing eon. Imagine waking up one day to find your GPS steering you into a lake, your smartphone's clock racing ahead by hours, or satellite signals dissolving into static. These aren't scenes from a sci-fi movie. They're the potential consequences if the speed of light, the silent engine driving modern technology, suddenly lost its constancy. From the atomic clocks synchronizing global finance to the lasers stitching together the internet's backbone, our world runs on the assumption that light speed is as reliable as gravity. But what if it isn't? The unsettling truth is that a shifting speed of light wouldn't just upend physics, it could quietly unravel the systems we depend on every day. Take GPS, for example. Every time your phone pinpoints your location, it's relying on a delicate dance of timing. Satellites orbiting Earth beam signals at light speed, and your device calculates distances by measuring how long those signals take to arrive. If light speed changed even slightly, those calculations would skew, throwing off your position by meters, then kilometers, then entire city blocks. The scary part, we might not notice immediately. Some theories suggest that if light speed shifted uniformly across the cosmos, local measurements could appear consistent, like a clock that's broken but still ticks at a steady, wrong pace. The error would only reveal itself when comparing data across vast distances or timescales, leaving future engineers scratching their heads over why their star maps no longer align. Telecommunications face an even thornier problem. Fiber optic cables, the highways of our digital age, use pulses of light to carry everything from cat videos to stock trades. Their design assumes light travels at a fixed speed through glass, about 200,000 kilometers per second. If that speed crept upward, data could arrive too fast, overwhelming buffers and crashing servers. Slower light, meanwhile, might throttle global bandwidth to a crawl. The internet's infrastructure is so finely tuned that even a fractional shift could cascade into chaos, like a symphony where every instrument gradually falls out of tune. Yet the most insidious impact might be on time itself, or at least how we measure it. Atomic clocks, the gold standard for precision, rely on the vibrations of cesium atoms, which are tied to the frequency of light they emit. If light speed drifted, those vibrations could change, warping our perception of time. Financial markets timestamp trades down to nanoseconds. Power grids synchronize across continents. A single second's discrepancy could trigger blackouts or flash crashes. The eerie part, we'd have no independent reference to spot the error. Time, as we define it, would simply stretch or compress, leaving us none the wiser until the mismatches piled up. But here's the twist, not all tech would fail equally. Some systems, like quantum computers, might adapt more gracefully. Their operations hinge on entanglement and superposition, phenomena already unshackled from classical speed limits. A variable speed of light could even unlock new computational tricks, like faster quantum communication or crisper entanglement. Meanwhile, civilizations of the far future might treat our fixed speed of light the way we view Newton's absolute time, a useful approximation that eventually gave way to deeper truths. The real lesson isn't just about vulnerability, it's about humility. Our entire technological empire is built on constants we've never rigorously tested across cosmic time. If light speed isn't the anchor we thought, it's a reminder that the universe owes us no guarantees. Every equation, every circuit, every line of code rests on assumptions that might one day need rewriting. And that's the beauty of science, not that it gives us final answers, but that it keeps us honest, always questioning, always recalibrating, always ready for the next revolution lurking in the data. Astrobiology's most fascinating question isn't just whether life exists beyond Earth, it's what form that life might take if the fundamental rules of physics were different. Picture a distant exoplanet orbiting a dim red sun, where the speed of light is half what it is in our solar system. Here, photosynthesis would operate in slow motion, with plants absorbing energy at a glacial pace, their leaves perhaps evolving to be wider, darker, or layered like solar panels to compensate. Vision itself would be altered. Creatures might see in a narrower or broader spectrum, their eyes tuned to wavelengths that behave differently under shifted light speed conditions. The chemistry of life, so delicately balanced on Earth, could take entirely unexpected turns. Amino acids might form at different temperatures, DNA-like molecules could spiral in unfamiliar ways, and even the concept of day and night might stretch or compress beyond recognition. But the real mind-bender isn't just how life would adapt, it's whether it could arise at all. On Earth, life's building blocks rely on precise interactions between light and matter. Chlorophyll captures photons with exquisite efficiency, and the energy barriers for key biochemical reactions are fine-tuned to our sun's output. In a universe where light travels faster, chemical bonds might form and break too quickly for stable complexity to emerge. Slower light, on the other hand, could leave reactions languishing, like a car engine struggling to turn over in freezing temperatures. Yet nature is resourceful. Life might find workarounds, exploiting exotic energy sources like tidal forces or geothermal vents, or even evolving entirely novel biochemistries based on elements we've overlooked. Consider the possibility of life in a high light speed universe, where photons zip past so fast that traditional photosynthesis is impossible. Organisms might rely on direct kinetic energy, harvesting particles from stellar winds or magnetic fields. Their eyes could detect radio waves or gravitational ripples instead of visible light, rendering our understanding of senses quaint by comparison. Or imagine a world where light crawls, a planet bathed in perpetual twilight, where creatures communicate through bioluminescent pulses lasting hours and metabolic rates slow to a near halt. These aren't just sci-fi scenarios, they're testable hypotheses. By studying extremophiles in Earth's harshest environments, deep-sea vents, acidic pools, frozen tundras, we catch glimpses of life's staggering adaptability. If organisms thrive here, why not in a universe with different physics? The deeper we dig, the more we realize how provincial our assumptions might be. Earth's life is built for Earth's constants, but if light speed is a variable, not a universal given, then the cosmic menu for life expands exponentially. Silicon-based organisms, plasma-based intelligences, even forms of life that harness quantum entanglement, all become plausible under altered physics. Astrobiology's greatest gift isn't just the search for aliens, it's the humility to recognize that life, in its infinite creativity, might rewrite the rules entirely. And that's the most thrilling possibility of all, not just finding life, but discovering that it's stranger than we ever dreamed. The first trillionth of a second after the Big Bang was a realm where normal physics took a holiday. In that inconceivable heat trillions of degrees hotter than the core of our sun, today space itself behaved like a funhouse mirror, stretching and warping beyond recognition. At these energies, some models suggest something extraordinary might have happened to light. Not just moving fast, but infinitely fast, as if the entire concept of distance momentarily blinked out of existence. Picture a newborn universe where a photon could cross the entire cosmos in zero time, connecting points that would later become galaxies billions of light years apart in an instant. This isn't just theoretical whimsy, it's a potential solution to one of cosmology's greatest puzzles. Why does the universe look so similar in all directions? The horizon problem has gnawed at scientists for decades. When we peer at the cosmic microwave background, the afterglow of the Big Bang, we see a sky of nearly identical temperature in every direction. But according to standard physics, those regions were once too far apart for heat to travel between them. Like two people stranded on opposite sides of an ocean, somehow wearing identical outfits without ever meeting. The usual fix is cosmic inflation, a theory proposing the universe expanded faster than light for a split second, smoothing everything out. But there's another way. If light itself had no speed limit in those first moments, distance wouldn't have mattered. Heat could have spread instantaneously, like ink dropped into a boiling pot, leaving that telltale uniformity we see today. Yet the implications go far deeper than solving a single puzzle. If light moved infinitely fast at the beginning, it would mean the speed limit we take for granted 299,792 kilometers per second isn't a fundamental law, but a later development, like a cosmic speed limit sign erected after the universe cooled. Some theories, like variable speed of light cosmology, take this idea seriously, suggesting light speed froze as the universe expanded, locking into the constant we know today. Others propose even wilder possibilities, that the early universe's physics operated under different dimensional rules, with extra dimensions curled up so tightly that light could take shortcuts, appearing to move faster than we'd measure in today's four-dimensional spacetime. The challenge is proving it. We can't recreate Big Bang conditions in a lab, but we might find clues in the quantum noise of the cosmos. Gravitational wave detectors could uncover ripples from the universe's first moments, carrying imprints of how spacetime itself behaved. The cosmic microwave background might hide statistical anomalies patterns too uniform to emerge without some form of faster-than-light communication in the past. Even particle accelerators, by smashing atoms at near light speeds, can simulate fractions of that primordial energy, offering glimpses into how matter and light interacted under extreme conditions. Skeptics argue that invoking infinite light speed is a band-aid for gaps in our knowledge, and they're not wrong to be cautious. Physics thrives on testable predictions, not just elegant stories. But that's what makes this frontier so electrifying. The Big Bang's first moments aren't just a historical curiosity, they're a laboratory for the most extreme physics imaginable. Whether light once broke its own rules or not, the mere possibility reminds us that the universe's infancy was far stranger than anything we see today. And that's the real gift of cosmology, not just mapping what we know, but discovering how much we've yet to understand. String theory paints a picture of reality far stranger than our everyday experience suggests. A cosmos woven from tiny, vibrating strings whose harmonies create everything from quarks to galaxies. But the real shocker isn't just the strings themselves, it's the stage they perform on. According to this radical framework, our universe might have not just the 3 spatial dimensions we know, but 10 or more, curled up so tightly we've never noticed them. Now here's where things get wild. If these extra dimensions exist, they could be hiding secret passageways for light, shortcuts through the fabric of reality where photons slip between dimensions like threads through a needle's eye. And if that's true, then the speed of light we measure in our familiar 4 dimensions might just be the tip of a multidimensional iceberg. Picture a hiker trekking across a mountain range. From their perspective, the path ahead winds and climbs, taking hours to traverse. But a bird flying overhead sees the same journey as a straight line, shorter, faster, unbound by the terrain's twists. In string theory's vision, light could be that bird. If photons occasionally dip into higher dimensions, their effective speed in our observable universe might appear to change, even if their true speed remains constant across all dimensions. Some models suggest that in the early universe's extreme energies, these extra dimensions were more accessible, like a crumpled piece of paper slowly flattening over cosmic time. Light racing through those tangled folds could have outpaced today's speed limit, then slowed as dimensions contracted, leaving us with the steady value we now call constant. The implications ripple through cosmology. Take the horizon problem, the puzzle of why opposite sides of the universe look so similar despite never having had time to exchange heat. Inflation theory solves this with a faster-than-light expansion spurt, but string theory offers another path. If light briefly exploited higher dimensions to bridge vast distances instantly, no inflation would be needed. Even dark energy, the mysterious force accelerating the universe's expansion, might find an explanation here. Some string theorists propose that what we perceive as dark energy could actually be gravity, leaking into extra dimensions, subtly altering how light and spacetime interact on cosmic scales. Yet the math is fiendishly complex. These extra dimensions aren't just unseen, they're unimaginably small, curled up at scales a billion times tinier than an atom. Probing them directly would require energies far beyond any particle collider we've built, like trying to map a cathedral's architecture by studying a single grain of sand. But indirect clues might lurk in the cosmos. If light speed was once different due to higher dimensional effects, ancient light from quasars or the cosmic microwave background could carry faint traces, anomalies in spectral lines or polarization patterns that defy 4-dimensional physics. Future telescopes, like the European Space Agency's Euclid mission, might spot these fingerprints hidden in the starlight. Skeptics argue that string theory's extra dimensions are untestable speculation, and they're not entirely wrong. Without direct evidence, these ideas remain dazzling hypotheses, not proven facts. But that's the nature of frontier science, to explore ideas so radical they blur the line between physics and philosophy. Whether string theory's hidden dimensions hold the key to light's mysteries or not, they remind us that the universe's rulebook might have chapters we've yet to read. And that's the real magic, not the answers we cling to, but the questions that keep pulling us forward into the unknown. Time crystals sound like something ripped straight from a physicist's daydream, structures that don't just exist in space, but pulse and repeat in time itself. Unlike ordinary crystals, where atoms arrange in predictable patterns like a grid of city blocks, time crystals break the symmetry of time, oscillating between states without any energy input, like a perpetual motion machine that defies the usual rules of thermodynamics. But here's where it gets even stranger. These bizarre structures might hold the key to detecting whether the speed of light has ever wavered across the ages. Imagine a cosmic metronome ticking not to the beat of human-made seconds, but to the deeper rhythms of the universe's own shifting laws. Think of a time crystal as a kind of quantum echo, a structure that preserves traces of the conditions in which it formed. Just as tree rings record years of growth or ice cores trap ancient air, time crystals could theoretically remember changes in fundamental constants like the speed of light by locking those variations into their rhythmic patterns. If light once traveled faster or slower in the distant past, the oscillations of a time crystal born in that era might carry subtle fingerprints of that difference, like a phonograph record playing back the universe's forgotten soundtrack. Researchers are already exploring how these crystals interact with light in lab settings, probing whether their unique time-keeping properties could serve as ultra-precise detectors for shifts in physics itself. The implications are staggering. If time crystals can act as cosmic clocks, they might reveal whether the fine structure constant, a number that hinges on light speed, has truly drifted over billions of years. Some theories suggest that in the presence of a variable speed of light, time crystals would oscillate at different frequencies depending on when and where they formed. A crystal born in the early universe's high-energy chaos might tick faster than one created today, its rhythm encoding the physics of a bygone era. It's as if the universe left behind a trail of clocks, each set to a slightly different time zone, waiting for us to decipher their discordant chimes. Of course, the challenges are immense. Time crystals are fragile, fleeting phenomena, often requiring temperatures near absolute zero and precise quantum control to stabilize. Scaling them up to cosmic proportions or finding natural analogs in the wild is a puzzle we're only beginning to tackle, but the potential payoff is irresistible. Unlike distant quasars or ancient starlight, which offer only indirect clues, time crystals could provide a direct, local record of physics evolution, like finding a diary buried in the fabric of spacetime itself. Skeptics argue that the idea is speculative, and they're not wrong. Time crystals are so new that we're still learning how they behave, let alone how to mine them for cosmic secrets. Yet that's the thrill of frontier science, the chance to turn wild ideas into tools for discovery. Whether time crystals ultimately reveal light's inconstancy or not, they remind us that the universe is richer, stranger, and more inventive than our boldest theories. And sometimes the most revolutionary breakthroughs begin with a simple question: what if time itself can remember? Neutrinos are the universe's most elusive escape artists, particles so ghostly they can slice through a light year of lead without a single collision. Born in the nuclear furnaces of stars, the violent hearts of supernova, or the searing dawn of the Big Bang itself, these phantoms carry stories from the cosmos's most extreme environments. But here's the twist: their very aloofness might make them perfect messengers for one of physics' greatest taboos, the idea that light's speed isn't the fixed constant we've always believed. If the rules of the game have changed over cosmic time, neutrinos could be the silent witnesses, their subtle quirks betraying secrets about a universe playing by different rules in its youth. Unlike light, which dances with matter through electromagnetism, neutrinos barely acknowledge the material world. They're governed by the weak nuclear force, a flickering shadow of an interaction that lets them slip through planets like a breeze through a screen door. This indifference to ordinary physics makes them ideal probes for testing whether nature's constants have shifted. Imagine two runners, one sprinting on a track, the other wading through a pool. If the track suddenly changes texture, the sprinter's time will falter, while the swimmer's pace might barely budge. Similarly, if light's speed has wavered, photons would show it plainly, while neutrinos less tethered to spacetime's usual rules might reveal a more nuanced story. The evidence is already tantalizing. In 2011, the Opera experiment stunned the world with data suggesting neutrinos might outpace light, arriving 60 nanoseconds earlier than expected from a beam fired 730 kilometers away. The result was later traced to a faulty cable, but the episode sparked a deeper question. Could neutrinos, under extreme conditions, behave in ways that hint at a deeper plasticity in physics? Some theories, like those linking neutrino oscillations to quantum gravity effects, suggest these particles might feel extra dimensions or space-time foam in ways photons don't. If so, their behavior could encode clues about whether light speed, or even the fabric of reality itself, has evolved. The real smoking gun might lie in relic neutrinos, the universe's oldest. These ancient particles, left over from the Big Bang, have been coasting through space for nearly 14 billion years, their properties frozen in time like insects in amber. If light speed was different when these neutrinos first raced across the cosmos, their energy spectra or oscillation patterns might carry faint echoes of that era. Detecting these whispers is a monumental challenge. Relic neutrinos are notoriously hard to spot, their signals drowned out by louder astrophysical noise. But next-generation observatories like the Ptolemy project aim to trap them using ultra-cold detectors, offering a window into the universe's first seconds. Skeptics, of course, point out the gaps. Neutrinos are notoriously slippery to study, and anomalies in their behavior often stem from measurement errors rather than new physics. Yet that's precisely why they're so compelling. In a universe where light's constancy is the bedrock of our understanding, neutrinos, with their refusal to play by ordinary rules, might be the only particles rebellious enough to reveal the cracks in that foundation. Whether they ultimately betray light's inconstancy or not, their mysteries remind us that the cosmos still holds cards it hasn't shown, and sometimes the quietest voices carry the loudest truths. Gravitational waves are the universe's most dramatic messengers, ripples in spacetime itself, born from collisions between black holes, the death spirals of neutron stars, and other cosmic catastrophes. These distortions race outward at the speed of light, carrying fingerprints of the events that created them. But what if that speed wasn't always the same? Hidden in their faint tremors could be clues that light's constancy is an illusion, a temporary rule in a deeper, more fluid cosmic story. Picture two runners in a marathon, one sprinting on solid ground, the other wading through shallow water. If the terrain changes, their relative speeds will shift, revealing hidden variations in the path. Gravitational waves and light are those runners. When a neutron-star collision lit up the sky in 2017, both gravitational waves and light arrived at Earth nearly simultaneously, confirming Einstein's prediction that they travel at the same speed. But what if, in the early universe's extreme conditions, that synchronization wasn't perfect? A fraction of a second's delay in ancient waves could betray a time when spacetime's ripples outpaced light, or vice versa. The next generation of gravitational wave detectors, like the Laser Interferometer Space Antenna LISA, will listen for whispers from the universe's first billion years, an era when physics might have operated under different rules. If light speed was faster then, gravitational waves from that epoch could arrive with subtle timing quirks, like echoes of a distant bell ringing out of sync. Even more tantalizing are primordial gravitational waves, hypothetical ripples from the Big Bang itself. If these relics are ever detected, their properties could reveal whether light once raced through a hotter, denser cosmos unshackled by today's speed limit. Yet the challenge is immense. Gravitational waves are already fiendishly hard to detect, their signals often buried in noise. Teasing out evidence of variable light speed would require comparing waves with light signals across cosmic time, a task like reconstructing a symphony from a handful of scattered notes. But the payoff would rewrite physics. Imagine confirming that gravitational waves from the early universe don't align with light's behavior today. It would mean Einstein's cosmic speed limit wasn't just broken, it evolved, bending to the universe's changing whims. Skeptics argue that such deviations could stem from other factors: intervening matter, instrument errors, or gaps in our models of neutron-star collisions. But that's the beauty of science at the frontier. Every anomaly is a thread to pull, a chance to question what we think we know. Whether gravitational waves ultimately reveal light's inconstancy or not, they remind us that the universe's deepest truths often hide in the quietest signals. And sometimes the most profound revolutions begin with a whisper. Cosmic inflation is one of the most breathtaking ideas in physics, a moment when the universe didn't just expand, but exploded outward faster than light itself, stretching from smaller than an atom to the size of a grapefruit in less than a trillionth of a second. This dizzying growth spurt solves some of cosmology's deepest puzzles, like why the universe looks so uniform in all directions. But here's the catch: inflation relies on a universe where space itself outpaced light speed, bending the rules of relativity just this once. Now imagine if light didn't play by those rules either. What if, in those first frenzied moments, photons weren't just left in the dust by expanding space? They were racing alongside it, or even faster. The math gets wild when you let light speed slide. Inflation's runaway expansion was a temporary loophole, a brief suspension of cosmic traffic laws to explain the smoothness we see today. But if light speed was also cranked up in the early universe, the entire plot thickens. Suddenly, inflation's breakneck expansion might not need to be quite so extreme. Light's own boosted velocity could have helped stitch distant regions together before they drifted apart. It's like two cars speeding down a highway. If both the road and the vehicles are accelerating, the distance between them changes in ways that defy simple intuition. Some theorists argue this could even explain why inflation's predicted gravitational waves haven't been spotted yet. If light's higher speed did some of the smoothing work, inflation's signature ripples might be fainter than we thought. Yet the implications go deeper than tweaking models. If inflation and variable light speed are two faces of the same cosmic coin, it forces us to rethink what the beginning even means. Inflation paints a picture of space unshackling itself from physics' usual constraints, a singularity of pure expansion. But if light speed was part of that liberation, then the early universe wasn't just stretching, it was rewriting its own rulebook in real time. Quantum fluctuations, dimensional physics, even the birth of time itself might have unfolded differently under these fluid conditions. The cosmic microwave background, that frozen snapshot of the universe's infancy, could be hiding layers of clues we've only begun to decipher. Skeptics push back hard, and for good reason. Inflation's predictions have matched observations with uncanny precision, from the distribution of galaxies to the subtle patterns in the CMB. Messing with that success by introducing another variable, light's inconstancy, risks complicating a theory that already works beautifully. But science isn't about preserving tidy narratives. It's about following the evidence, even when it leads to uncomfortable places. Whether inflation and variable light speed are rivals, allies, or something stranger altogether, their tension is a reminder that the universe's first moments are still the wildest frontier we've ever dared to explore. What if the speed of light isn't just a law of physics but a line of code? The simulation hypothesis, the mind-bending idea that our universe might be an artificial construct, offers a radical lens to view light's potential inconstancy. Imagine a vast cosmic computer, its processors straining under the weight of simulating every star, every atom, every photon racing through space. Even the most advanced system would have limits. Could variations in light speed be the equivalent of lag, tiny imperfections in the rendering of reality, as the simulation struggles to maintain consistency across its virtual cosmos? This isn't just philosophical musing. Modern video games offer a startling analogy. When a game world grows too complex, frame rates drop, textures glitch, and physics engines stutter. Players call it rubber banding when characters or objects suddenly snap between positions as the system catches up. Now scale that up to universal proportions. If our reality is simulated, a fluctuating speed of light might be the universe's version of a processing error, a telltale sign that even the architects of existence have to cut corners. Some theorists point to quantum indeterminacy as another potential artifact, the universe's way of saving computational power by only defining properties when observed. Why couldn't light's speed be another variable left intentionally fuzzy to reduce the simulation's load? Yet the implications go far beyond glitches. If physics constants are adjustable parameters in some grand cosmic code, it reshapes how we think about reality itself. The speed of light wouldn't be a discovery, it'd be a design choice, one that could be tweaked in different versions of the simulation. This might explain why the universe's constants seem so finely tuned for life. Instead of cosmic coincidence, it could be intentional calibration, like a programmer dialing in the perfect settings for a stable virtual world. Even the mysterious axis of evil, those odd alignments in the cosmic microwave background, could be fingerprints of a coordinate system baked into the simulation's framework. Skeptics, of course, dismiss this as speculative fiction. Without direct evidence, the simulation hypothesis remains untestable by conventional science. But its value isn't in proving where digital construct sits in challenging our assumptions about what's possible. If even a fraction of these ideas hold water, they force us to confront an unsettling truth. The laws we treat as absolute might be more like user agreements, subject to change without notice. Whether the universe is a simulation or not, the mere possibility reframes light's speed from an eternal truth to a variable waiting to be debugged. And that's the real power of this idea, not in the answers it provides, but in the doors it kicks open. After all, if reality has a source code, who's to say we can't one day read it? Relic radiation isn't just a cosmic afterglow, it's a time capsule, a whisper from the universe's first breaths. This faint hum, known as the cosmic microwave background, or CMB, blankets the cosmos, a cooled remnant of the Big Bang's searing heat. But woven into its delicate patterns could be clues that light once played by different rules. Imagine this radiation as a fossilized snapshot of the universe at 380,000 years old, the moment atoms formed and photons finally broke free to travel unimpeded across space. If those primordial photons raced faster than light does today, their journey would have left subtle distortions in the CMB's fabric, anomalies invisible to the naked eye, but detectable with the right tools. Hunting these echoes isn't just about building better telescopes. It's about redefining how we read the universe's oldest text. The CMB's temperature fluctuations, mapped in exquisite detail by missions like Planck and WMAP, aren't random. They're a cosmic barcode, encoding the density variations of the early universe. But what if some of those fluctuations aren't just from clumps of matter, but from light itself breaking its own speed limit? Some theorists suggest that faster light in the early universe would have smoothed out certain irregularities while amplifying others, leaving behind a statistical signature, like a baker's thumbprint pressed into the dough of spacetime. The challenge is distinguishing this fingerprint from the noise of cosmic variance, interstellar dust, and instrument limitations. Enter next-generation observatories like the Simons Array and CMB-S4, designed to scan the sky with unprecedented precision. These projects don't just aim to map the CMB's temperature, they're chasing its polarization, the faint directional twist imprinted on photons as they scattered off the first atoms. If light speed varied, it could have altered how those twists propagated, leaving telltale swirls in the polarization patterns. Think of it like analyzing the ripples on a pond long after the stone was tossed. The shape and spacing of the waves betray the force and angle of the original splash. Similarly, the CMB's polarization might reveal whether light's splash into the cosmos was gentler or fiercer than we've assumed, yet the stakes are higher than just confirming a theory. If relic radiation betrays a variable speed of light, it wouldn't just tweak our models, it would force us to rethink how we measure the universe's age and expansion. The CMB is the yardstick we've used to calculate the cosmos's 13.8 billion-year history. But if light speed was different when that radiation was emitted, our cosmic timeline might need recalibrating, like adjusting a grandfather clock that's been ticking at the wrong rate for centuries. Even dark energy's mysterious influence on cosmic acceleration could be reinterpreted. What if the universe isn't expanding faster, but our ruler's been shrinking? Skeptics argue that the CMB's uniformity is too perfect to accommodate such wild ideas. After all, inflation theory already explains the smoothness we observe without invoking a shifting speed of light. But science thrives on tension between the established and the speculative. The CMB's secrets aren't just locked in its temperature or polarization, they're hidden in the correlations between them, the way its patterns intertwine like threads in a tapestry. Untangling those threads might require more than incremental improvements in sensitivity. It could demand entirely new ways of thinking about light, time, and the universe's memory of its own birth. What makes this search so electrifying isn't just the potential discovery, it's the audacity of the question. We're not just asking how the universe began, we're asking whether its very laws were written in erasable ink. And as we train our telescopes on those ancient photons, we're not just observers of the past, we're detectives sifting through the cosmos's oldest crime scene, searching for evidence that the constants we hold sacred might have once been anything but. Future experiments to test light's constancy aren't just about refining measurements, they're about rewriting the cosmic rulebook with tools so precise they border on science fiction. Picture atomic clocks so accurate they'd lose less than a second over the entire age of the universe, floating in the quiet of space, far from Earth's vibrations and atmosphere. Projects like NASA's a Deep Space Atomic Clock and the European Space Agency's Atomic Clock Ensemble in Space aim to do just that, comparing timekeeping across vast distances to spot even the tiniest deviations in light's behavior. These aren't your grandfather's pendulum clocks, they're quantum marvels, using lasers to trap atoms in states so stable they could detect a shift in light's speed as subtle as a grain of sand altering Earth's orbit. Then there's the hunt for anomalies in the cosmic microwave background, the universe's oldest light. Next-generation telescopes like the Simons Observatory and CMB-S4 will map this radiation with pixels 100 times sharper than previous efforts, searching for patterns that defy standard physics. Imagine combing through a tapestry woven 14 billion years ago, looking for threads pulled by a speed of light that didn't play by today's rules. Some theorists predict that if light once traveled faster, its fingerprints would linger in the polarization of these ancient photons, twists and curls in the light's orientation that no other process could explain. But the real game changers might be quantum networks, experiments that exploit entanglement to test physics in ways previously unimaginable. In labs across the globe, scientists are building systems where particles remain mysteriously linked across kilometers, even as Earth hurtles through space. If light speed has shifted over time, these entangled pairs could reveal it through subtle mismatches in their quantum states, like synchronized dancers suddenly falling out of step. The catch: this requires isolating the experiment from every conceivable interference, from cosmic rays to magnetic fields, a challenge so immense it makes diffusing a bomb look trivial. And let's not forget pulsars, nature's own cosmic lighthouses. These spinning neutron stars beam radio waves with metronomic precision, and arrays like the Square Kilometre Array will soon monitor thousands of them, turning the galaxy into a colossal speed trap for light. If photons from distant pulsars arrive a fraction of a nanosecond early or late compared to nearby ones, it could hint that light speed varies with space-time's curvature or the universe's age. It's like using the stars themselves as a stopwatch, one that's been running since before Earth formed. Yet the most tantalizing experiments might not even exist yet. Some physicists speculate that future gravitational wave detectors could catch echoes of black hole collisions from the early universe, comparing their arrival time with light to see if gravity's ripples once outpaced photons. Others dream of lab-made mini-Big Bangs in particle accelerators, recreating conditions where light speed might flicker like a candle in the wind. The answers won't come easy, but that's the thrill of the chase. Whether these experiments confirm light's constancy or crack it wide open, one thing's certain: the universe has never been under such precise scrutiny. And if history's any guide, the closer we look, the stranger reality becomes. Changing the speed of light isn't just adjusting a number, it's rewiring the circuitry of physics itself. For every scientist willing to question light's constancy, there are others who see the idea as a bridge too far, a risk that could unravel centuries of carefully built theory. The resistance isn't just about stubbornness, it's about the monumental stakes. Einstein's relativity is the scaffold holding up modern cosmology, from black hole predictions to the GPS satellites guiding your morning commute. Tweak light speed, and suddenly, the equations governing everything from stellar evolution to quantum field theory start sprouting question marks like cracks in a windshield. Take the fine structure constant, that delicate ratio tying together light speed, Planck's constant, and the charge of an electron. It's a number so precise that if it varied by even a fraction of a percent, stars might not fuse hydrogen, and carbon, the backbone of life, could become unstable. Critics argue that if light speed had truly shifted over cosmic time, the fine structure constant would have left glaring fingerprints in the atomic spectra of distant quasars or the nuclear reactions powering stars. Yet the evidence remains ambiguous, a Rorschach test where some see revolutionary clues and others see measurement noise. The quasar spectral lines that hint at variation could equally stem from interstellar gas clouds or calibration quirks in our telescopes. When the stakes are this high, skepticism isn't just healthy, it's essential. Then there's Occam's razor, the principle that the simplest explanation is usually the right one. Inflation theory, for all its wildness, elegantly solves the horizon problem with a single exponential growth spurt. Introducing a variable speed of light feels like adding a second engine to a rocket that's already flying unless there's undeniable proof it's needed. As one physicist quipped, you don't tear down a skyscraper because someone thinks the foundation might be uneven. You bring a better blueprint. And so far, no alternate blueprint has matched relativity's predictive power. When gravitational waves from colliding neutron stars arrived within seconds of their light counterparts in 2017, it wasn't just a victory for Einstein. It was a gut punch to any theory suggesting light speed could waver under modern conditions. Yet history whispers a cautionary tale. When Einstein himself appended Newton's absolute time, the backlash was fierce. Leading physicists dismissed relativity as nonsensical and a mathematical swindle. Even Max Planck, Einstein's later champion, admitted that new scientific truth doesn't triumph by convincing its opponents, but because its opponents eventually die. The irony is thick. Today's heresy often becomes tomorrow's dogma, provided the evidence holds. The question isn't whether challenging constants is radical, but whether it's radical enough to survive the gauntlet of peer review and experiment. What's fascinating isn't the divide itself, but what it reveals about how science evolves. The skeptics aren't gatekeepers, they're stress testers, forcing every new idea to prove its worth against the collective wisdom of centuries. And the rebels, they're the ones daring to ask if that wisdom might be wearing blinders. Whether the speed of light's constancy falls or stands, this tension between tradition and revolution is how physics inches closer to truth. After all, the universe owes us no guarantees. The only certainty is that our maps of reality are always, inevitably, incomplete. Hollywood loves to play fast and loose with the speed of light, starships zipping between galaxies in hours, time travelers bending reality with flashy gadgets, even heroes dodging laser beams in slow motion. But when we strip away the cinematic spectacle, what's left is a far stranger truth. Light's behavior in the real universe defies both intuition and fiction. One of the biggest myths, that faster-than-light travel is just an engineering problem waiting to be solved. In reality, relativity isn't a speed limit sign you can ignore with enough rocket fuel. It's baked into the fabric of spacetime itself. If light's speed varied over cosmic history, it wouldn't mean starships could suddenly break the rules. Instead, it would rewrite the very definition of distance and time, turning interstellar navigation into a puzzle far more complex than any sci-fi script. Then there's the time travel trope, the idea that exceeding light speed would send you backward through history. While relativity does allow time dilation where high-speed travelers age slower than those at rest, a changing speed of light wouldn't magically unlock DeLorean-style paradoxes. In fact, if light moved faster in the past, the implications would be subtler but more profound. The universe's timeline might stretch or compress, altering how we measure its age without creating causal loops. Imagine a clock that ticks slower in a high-altitude plane due to gravity. Now scale that effect across billions of years. The result isn't a time machine, but a cosmic recalibration where the when of events depends on the how fast of light itself. Another persistent myth is that light speed is about photons racing through space like sprinters on a track. In truth, it's a fundamental property of electromagnetism, tied to the permittivity and permeability of the vacuum itself. If light speed changed, it wouldn't mean photons got lazier. It would suggest the stage they perform on has transformed. Think of it like sound traveling faster in water than air. The difference isn't in the sound waves, but the medium they move through. A variable speed of light implies spacetime's fabric might have been stiffer or looser in the past, reshaping how energy and information flowed in the young cosmos. Perhaps the most seductive misconception is that a shifting speed of light would make the universe feel dramatically different. No sudden flashes, no shattered physics, just a quiet reworking of the cosmic fine print. Distant galaxies might be slightly closer or farther than we thought. The afterglow of the Big Bang could carry hidden asymmetries, but your morning coffee would still brew the same way. Constants aren't just numbers, they're relationships, and changing one doesn't necessarily collapse reality. It might just reveal a deeper layer we've yet to fully grasp. The real takeaway: science isn't about debunking wonder, it's about redirecting it. The truth of light's potential variability isn't less thrilling than fiction, it's more so. Because the universe doesn't need warp drives to astonish us, it's already rewriting its own rules in ways we're only beginning to decode, and that story, the real one, is stranger than anything Hollywood could dream up. The moment we unlock the ability to tweak the speed of light, we're not just adjusting a number, we're reaching into the cosmic control panel and pressing buttons labeled "Do Not Touch." The ethical weight of this power is staggering. Fundamental constants like light speed aren't arbitrary settings. They're the invisible threads stitching reality together. Tug on one, and the whole tapestry might unravel in ways we can't predict. Imagine a civilization handed the keys to gravity, electricity, or nuclear forces without understanding the consequences. Now amplify that by the entire framework of spacetime itself. History offers sobering lessons. When scientists split the atom, they unlocked energy to power cities or destroy them. The same equations that gave us clean nuclear energy also built weapons capable of erasing civilizations. And that's just manipulating matter. Light speed is deeper. It's the backbone of causality, the glue holding past, present, and future in sequence. If we could speed up light locally, would we risk creating pockets where cause and effect flip, a region where fires extinguish before they're lit, or messages arrive before they're sent? The paradoxes aren't just theoretical, they're existential. Then there's the arrogance of assumption, the idea that we'd know how to wield this power responsibly. Our track record with ecosystems, climate, and even artificial intelligence shows how often unintended consequences outpace our foresight. A lab experiment tweaking light speed might seem harmless, but what if it triggers a cascade effect? Photons are messengers of the universe. Change their rules, and you alter how stars emit energy, how plants photosynthesize, even how our own neurons fire. The butterfly effect wouldn't just apply to weather, it could rewrite physics on a galactic scale. Yet the allure is undeniable. Mastery over light speed could revolutionize technology, faster than light communication, warp drives, or energy harvesting beyond our wildest dreams. But here's the catch. Those advancements assume we'd survive the learning curve. Early chemists accidentally discovered explosives. Early geneticists couldn't foresee CRISPR ethical dilemmas. Playing with constants is a gamble where the stakes aren't just progress, they're existence itself. Perhaps the most unsettling question isn't whether we can tamper with light speed, but whether we should. Science thrives on exploration, but some frontiers might demand restraint. The universe has run on these rules for billions of years, fostering galaxies, stars, and life. If we're ever handed the wrench to adjust them, the real test won't be technical, it'll be moral. Because power isn't wisdom, and understanding isn't permission. Sometimes the greatest scientific act isn't pushing forward, it's knowing when to step back. For centuries, the speed of light has stood as physics' unshakable foundation. A number so precise, so unchanging, that we've built our understanding of reality upon it. But as we've journeyed through the cosmos's deepest history, from the first sparks of the Big Bang to the quantum foam frothing at spacetime's edges, a humbling truth emerges. Even the most sacred constants might carry hidden flexibility. The evidence is flickering at the boundaries of our knowledge, quasars whispering spectral anomalies, ancient starlight hinting at forgotten rules, black holes warping the very fabric of causality. Yet the absence of proof is just as telling. For every tantalizing clue, there's a counterargument, a measurement quirk, a simpler explanation waiting in the wings. This isn't failure, it's science at its most vital, the tension between doubt and discovery that drives every great leap forward. What makes this debate so electrifying isn't just the science, it's the philosophy humming beneath it. Constants aren't just numbers, they're mirrors reflecting how we see the universe's workings. To question light's constancy is to ask whether nature's laws are etched in stone or scribbled in sand, reshaped by time's invisible hand. Imagine a cosmos where the rules themselves evolve, where today's equations are but a snapshot of a grander, ever-shifting tapestry. It's a vision both exhilarating and unsettling, reminding us that every certainty is a question waiting to be asked. Yet here's the beautiful paradox. Even if light's speed proves immutable, the act of questioning it has already reshaped our cosmic perspective. We've built sharper telescopes, finer clocks, deeper theories, not because we knew the answers, but because we dared to wonder. That's the true heartbeat of exploration. Whether the next breakthrough comes from a lab's meticulous measurement or a lone thinker's midnight epiphany, one thing's certain: the universe rewards curiosity. So stay restless, stay skeptical, and above all, stay enchanted by the mysteries still glowing just beyond the light we think we know. The adventure's far from over, and you're part of it. Drop your wildest theories in the comments. Hit like if you're ready for the next cosmic revelation, and subscribe to join us as we keep chasing the universe's biggest secrets. The next chapter starts now.